Okay. So yeah, again, my name is Sarah McAllister. I work for the Forest Service for the U.S. And my background is really that I am a research mechanical engineer. So as Mark had said, things are going to get a lot more technical after the break, so I apologize for that. But it's a warning. So my job basically is to understand what we don't understand, to ask those questions, to figure out where our gaps are in the knowledge, and then try to answer them. So it turns out there's a lot we don't know. As was mentioned earlier this morning, live fuels is a big question mark. We know that it is an unknown, and we're working on it, but you know, it's a hard problem, so we're getting there. But that's not what I'm going to talk about today. The talk today is going to be mostly on the other big unknown is what's different with big fires. So clearly they seem to burn very differently than small fires, and we want to know why. And we think that has a lot to do with what goes on above the fire, in the fire plume. So we're going to look at the burning rate and how that changes with the different things that happen in the plume above. So the reason why we look at burning rate is that it is part of the fire spread process. So our research is really focused on breaking down fire spread into its component parts. So it's really, fire spread is a series of ignitions. You have to have an ignition event in order to even have a fire, right? So once a fuel burns, it ignites, and then it releases energy at a particular rate, and that is that burning rate question, or the energy release rate question. And some of that energy is then transferred as heat to unburnt fuel ahead of it, and enough heat has to be transferred for ignition to occur and to continue the fire spread process. So burning rate is part of that process, and it is sort of the motivation for why we're looking at what we're looking at. And as also Mark alluded to, it also kind of gives you some idea of like what kind of tactics you can and cannot use based on that burning rate. So large fires seem to burn differently. So these pictures are actually from a fire that happened last summer in 2016, just outside of Missoula. So the picture on the left over there was taken pretty much out of the back door of our research lab. So we had a pretty good sort of view every day of this fire. So it started in about mid-July, and it burned several months into October until it started to snow. We never did actually have it fully contained. And every afternoon, we got a smoke plume that looked just like that. So these are the kind of fires that we're talking about. They get big. The smoke plume tends to get very, very big. And the reason why these fires, we think, tend to do a lot different than what we're used to or what our models can predict is that they're not simple lines of fires. So all of our models and our intuition, our instincts mostly apply to line fires where there's a finite width to them, right? They ignite and they burn out and they sort of spread in a propagating front. But when you get into heavy timber, where there's big logs or there's a lot of duff and litter on the ground, with things that burn for a very long time, that line fire turns more into an area that's on fire. And so when you have an area that's on fire and it gets wider and wider, the plume of smoke above it gets wider and wider. And so as that plume gets wider and wider, fresh air can't get entrained and pulled up into that smoke plume, so it has to come from somewhere. And so, as we'll see, it induces quite a bit of wind that can fan the flames. So this is what we think is going on, and so we are trying to do some experiments to help us sort of understand it a little bit better. But for fun, we are going to look at a video that really kind of got us started thinking about this problem. So this is from a camera that was put inside of a prescribed burn. And so it was a prescribed crown fire. So there's a little bit of sound going on in the background, but occasionally you'll see a helicopter fly in the background. So they're doing helicopter ignitions. And this movie is a few minutes long, but everybody likes to watch fire in this room, so I think we'll be okay watching it. But so at first, we can see that there's quite a bit of ground fuel down, some big logs. There's some grasses and shrubs and brushes. And we first see, as we're seeing right now, a surface fire kind of come through. And it, does kind of as we would expect. Just sort of burns on up the hill, doing its thing. I'm just going to let it play. But it's pretty tame, just a prescribed burn, what you would expect. The live fuels are involved, clearly. Those green grasses are burning. It's pretty much just a normal fire. I think I'll take this opportunity to see if I can't fast forward just a little bit without, I don't know if I'm going to be able to. I'll let it play. I'm worried that if I fast forward the video, it's going to skip to the next slide. What you'll see as the surface fire passes, some of the larger, heavier fuel does stay ignited, and it burns for a little while. It's kind of more toward the background. But it largely kind of dies down for a little while. So believe it or not, this is a lot of research. We sit and watch a lot of videos of fire and try and understand what's going on. But this helps us wonder, like, what are we seeing and why are we seeing it? I don't know if everybody can hear, but there is a helicopter circling on this in the background. There's obviously some wind, but it's also on a slope, so you're getting some of that just induced wind because it's going up a hill. But I mean, the ground is mostly just smoldering at this point, right? But you've got some of those larger logs still flaming, and you would think at this point the fire is done. And then something changes. Starting to get a little more wind. That pile in the back is burning a little more vigorously. Starting to walk up the backs of the trees a little bit more. All this a few minutes after the main front passed. little bit more wind. Smoke clears a little bit for some reason. A little more wind. And then this happens. All of that surface fuel that you thought was out reignites and starts burning again. Quite intensely at times. She thought all the fuel was consumed, but yet this can still happen after the surface fire passes. So obviously conditions like this are not something that we can recreate on a daily basis, right, out in the field, or we can't really control these things. So we have to do a lot of experiments, and so we have a research lab dedicated to doing experiments to help us kind of understand this kind of fire behavior. I think it mostly dies down after that. We'll move on. So we can't make these conditions in the lab or in the field very regularly. So what we do is we have to find a way to simulate that. And so, I mentioned that the air can't be pulled into the plume above these large fires because they're just simply too wide. So a little bit of air can get pulled in, you get some fresh air into your plumes, but ultimately they're too big. So what we do in the lab is to put an artificial barrier up, and that's just simply the use of a chimney. What's really kind of amazing is that we've had chimneys in our homes for thousands of years, but we've never really looked at how they actually influence the behavior of the fuel that's actually in our fireplace or underneath it. So what we're doing is a bunch of experiments. This is still sort of a work in progress, right? This is research. So we're looking at how different heights of chimneys affects how the fuel underneath it burns. And because it's research, we really want to be able to control very finely the fuel that we burn. So we use what are called wood cribs. And there's a picture of a wood crib under our little chimney here, but they're basically just ordered cross piles of wood sticks. And this allows us to change the fuel configuration in any way we really want to. We can change the fuel thickness, how densely it's packed, how tall it is, how wide it is, like that fuel bulk density we can really kind of finely tune, because if we were to use like a tree or a shrub or whatever, we're given what nature has given us, right? So we can't really do very controlled experiments with that. So we have to use these artificial fuel beds. So far we've done a lot of experiments with 3 different fuel thicknesses. We've conditioned them to make them very dry, so we're looking at a very constant and uniform moisture content. And we actually prop them up off of our little weighing platform a little bit because previous experiments have shown that that height above the ground can really make a difference. So we've picked a height that's sufficient so that it's not a factor. Again, we're trying to limit our variables here so we can tweak them one at a time. And we ignite them actually by dunking them in isopropyl alcohol so we can get them to burn all at once to try to get them as uniform as possible. So in order to get the burning rate, what we do is we measure the weight of the crib as it burns. So we've got 3 different load cells underneath that platform that we continuously record the mass of the fuel bed. And you may note that this whole thing is on a cart. So we actually ignite the crib out from underneath the chimney, let the sticks get going and burn, and then we push it under the chimney. It's not a good idea to burn flammable fuel vapors in a confined spot, so we learned that the hard way. So that's why we do it in that order. So we've actually tested quite a bit of different configurations of our fuel beds. So far we've tested 17 different fuel bed configurations. This is a very busy table, but you'll see that there's different stick thicknesses, different stick lengths, which gives us a different fuel bed width. We vary the configuration quite a bit by varying the number of sticks per layer and the number of layers, and that gives us a fuel bed porosity. So this is similar to a bulk density, but it's a term it's used quite frequently in the literature for these crib fuels, and that helps us gives us an idea of whether the fuel bed is very tightly packed or very loosely packed. If it's very tightly packed, then it's ventilation limited, so its burning rate it's very choked, it's very smoky, it's very kind of gives off a lot of just gross white smoke because it doesn't have enough air to very thoroughly burn. So this happens when the porosity is below a critical value of like 0.05. So the fuel beds that have low porosity are listed there. And we've also tested a bunch of fuel beds that are not densely packed, that are much more loosely packed, much more fluffy fuel beds that are not limited by this airflow through it. And we're currently testing a bunch of different chimney heights, work in progress. We're almost through testing that whole series with all of the different chimney heights to see what effect that has. So I have another video. This one is showing these actual experiments. So let me just push play here on it and tell you what you're seeing. So we're looking at two experiments side by side. The one on the left, if this will play, here we go. The one on the left is without a chimney, and the one on the right is with the chimney. They're the same exact fuel bed otherwise. And you'll see as this goes, quite a bit of different behavior. So if you can see it, the graph on the bottom there shows what the mass, the change in the mass looks like. So the orange one is for the one under the chimney, and the blue one is the one outside of the chimney. And you can see those two plots diverge quite differently, quite quickly. So you can see with the chimney on the right that the fuel bed burns much more vigorously than without the chimney. So that effect of limiting the entrainment in the plume above it really has a direct effect on the fuel bed underneath it, which could create a sort of a feedback mechanism, right? So if big fires are big, they can get bigger and burn more vigorously with this chimney. So you can see quite a bit of a difference here. So looking at actual numbers, because again, I'm an engineer, I like these numbers. Here we're looking at what happens so we tested 17 crib designs. So I've broken up them into a few different graphs so you can all see them a little bit more clearly. So 11 of our crib designs behaved kind of as we expected. So the bottom axis there is the chimney height. So as we went up and added more and more chimney, and the y-axis is the normalized burning rate. So what I did was I took the burning rate that we measured for the different chimney heights and divided it by what it was without a chimney. So by definition, all of my graphs should start at 1. So no chimney, you get a normalized burning rate of 1. So for these different crib designs, we see quite a bit of an increase in the burning rate. In some cases, it's up to 3 times more. So with this reduced plume entrainment, you can get a tripling of the burning rate of the fuels underneath it with no other change. So just this setup in the atmosphere can create quite a bit of a different burning condition. So 11 of these crib designs did kind of as we expected. So here's the other group. These were a little bit less dramatic than that first group, but sort of the same general kind of increasing trend with the chimney height. However, we had a handful, 6 of them that did not burn as we expected. So we're looking at the same plot here with the normalized burning rate and the chimney height, and that black horizontal line marks the value of 1. So for some of these, our burning rate actually dipped below what it was without the chimney height, without the chimney there. So this was puzzling, and we wanted to figure out why. But let's first talk about sort of the easier answer. So why did we see an increase in the burning rate? Well, so with this chimney, or with these wide plumes that restrict our airflow, we get a very tall column of hot gases. So because you've got this really tall column of hot gases, they're very low density, it has a very low pressure right underneath it. So compared to the atmospheric pressure, there's a big pressure difference, which forces a lot of airflow down on the ground, induces the wind into the fire. this is very important if your fuel beds are very dense, because you're blowing a lot more air in it. So you're essentially like leaning out the fuel and air mixture in there, letting it burn more thoroughly. But it also increases, it's called the char oxidation rate. So you're essentially blowing on the coals. I mean, if you've ever played with a campfire and blown on the coals to get it to burn better, that's exactly what's happening. So this is important because it actually can promote flaming over smoldering. So this is what we saw in that video of the prescribed fire, right? So we're inducing a wind. The stuff that was just barely smoldering and kicking around that you thought was out started flaming again because of this increased ventilation. So this could be very important because this will consume fuels that wouldn't normally be consumed, because you might just, your big log might just smolder and go out after a while. But with this induced airflow, you're going to get your bigger, heavier fuels, your duff, burning and flaming more. So it's going to increase the amount of fuel consumed as well. So those two variables are important, right? So your char oxidation is going to be very dependent on how much surface area you have. And that blowing of the air into your condensed fuels is going to be dependent on that porosity. So this graph here just sort of demonstrates that we think we kind of have a grasp on some of the physics of the peak burning rate. So those individual points are just the peaks off of all of the plots that we had seen in the last few slides. So this tells us, I think we have a pretty good grasp on why we're seeing the increase and how much it's going to increase. But the problem is that decrease case. So these two figures are, again, the same fuel bed comparing with and without a chimney. So without a chimney, that fuel bed burns very uniformly, very vigorously. It seems like it's doing quite well, but you put it under a chimney, and you'll notice that only the inner core is burning, and that the outside is not. It's not even charring. It looks like it's completely untouched by the fire. And so that increased ventilation has a drawback, because all that wind is cold air. So you're blowing cold air on your fuel and cooling it down. So you're not heating up your fuel to get it to ignite and burn. So that could be limiting that effect. And in some cases, it's quite dramatic. This is one of the cases that really only burned in just a very tight little spot, leaving the rest of the fuel bed untouched. What's crazy is I do all of my experiments over and over again to see what happens, just to make sure it wasn't a fluke. This happened every single time I did this experiment. It looked exactly the same. So something's a little bit different. The other thing we started to see, you can see if you look very closely at the flame in this picture. So there's quite a bit of airflow that comes through, and it's almost like blowing out the flame. There's almost too much air for it to actually consume all of the fuel. So there's too much air moving too fast. So all of the fuel gases and the flames are actually burning removed from where the solid fuel is. So you're not getting the heat transfer from the flames back to the fuel to help feed back the burning. So there's kind of a couple of things going on there that we think are accounting for this decrease in our fuel bed. So what's different between those few cribs? This is a very busy slide. I'm just going to keep it short. So those ones that burned very differently were all the physically shortest fuel beds. So they're going to be the most susceptible to that cold air because there's just not as much height there. But they also have a unique characteristic that they all have very low Q star. So Q star is a term that's used in fire protection engineering a lot that helps correlate flame heights. So when your flame height is very big relative to the width of the fuel bed, your Q star is more than 1. And this is kind of what you would think of as normal fires, like your candle flame or really any, like your campfire or whatever, should fall into this regime. But when your Q star is very small, your flame height is very short relative to the width of what's burning. And then you end up with getting these little, it's called distributed flamelets, little flames and pockets that happen in little places. So it's very possible that this is putting a limiting factor on our getting fires too big. So big fires are big because they're big, but there's a limit to that effect. So when it actually starts getting really, 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 really big, it may start putting a negative feedback on what's happening, but otherwise you're getting a positive feedback. There's more here, but that's kind of the gist of, I think, what we're seeing is that there is this feedback mechanism if you get the right conditions with the right size of fire that creates a positive feedback with the airflow on the fuel bed, but positive feedback only to a certain point, that at some point you will end up reaching a threshold and end up taming it back down. But the question that we're running into with those unique fuel beds is, what exactly do we call the burning rate? So this is something I'm struggling with. I need to do more experiments here. But this is what the data typically looks like. The dashed lines are the raw mass data. So you light it and it goes down. The mass decreases. And so the solid lines are the rate. So if you were to take a curve fit of those dashed lines and then take the slope of that is what you get as the rate. So when I talk about the burning rate, it's usually the peak of those solid lines. And they're often the steadiest value, right? It's the value that you would see kind of the most. You light your fire, it kind of starts to build. You get a certain burning rate for a little bit of, maybe 30 seconds, maybe a minute, and then it starts to die down as the fuel burns out. But it's very clear when you're talking about a burning rate what you're talking about here. But those really weird fuel beds do something different, depending on whether or not you're ventilating it with this chimney or not. So you get both a peak and a steady value that don't coincide. So it really makes you wonder, what are we actually talking about for burning rate for these really weird fires? So this is an ongoing research project and things we have to think about. So there is an interesting sort of interplay here on scale. So just to sort of summarize it, we need to understand what's different between large and small fires, and so we can actually do these better in the lab, do the experiments better in the lab, have better understanding of what's going on, be able to put this into our model better. And one of those potential things that we're looking at is this idea of reduced plume entrainment. And we did a bunch of experiments looking using a chimney to mimic this, and we saw that there are certain conditions that can happen where you're going to massively increase the burning rate of the fuel underneath it by, like I said, more than 3 times. And that will create a positive feedback. So the bigger the fire, the more you're going to see this, the bigger the fire it's going to be because you're increasing your burning rate. But it seems like that there's a limit to it eventually. But future work, we still have pretty big unanswered questions, is deciding how big is big. When do you get this transition to this reduced plume entrainment feedback mechanism? Because obviously it doesn't happen on all fires. So that's a pretty critical question to ask in order to be able to tell people, hey, watch out for this. We need to understand what's going on for those limiting conditions. I said the lower Q stars, and finding sort of the optimum of what, how tall of a chimney for how big of a fuel bed do we need. So I think I'm pretty much running out of time. So just say thank you, and thanks for inviting me. Thanks for listening.